Hello everyone, thank you for coming to my presentation today. I'm Yan Liu. I'm now a fifth-year PhD student from the Ohio State University. Today, my presentation will focusing on SB16 mediated nanoparticles enabling accelerated kinetics in cyclic methane conversion to syngas at low temperatures. This graph here shows the energy consumption in the United States in the past 30 years. As shown on this figure, the consumption of natural gas is keep increasing and will keep this trend in the foreseeable future. And it will reach up to 35% in 2050. However, due to the chemical properties of methane, including its negligible electron affinity and low polarizability, it is difficult to directly convert methane to liquid fuels. So for now, to convert methane to chemicals, in industry, we use gas-to-liquid process. In the most widely used conversion pathways from natural gas to industry products, the process will go through an intermediate, the syngas, which is a mixture of mainly H2 and CO. The syngas can be converted to valuable chemicals, such as methanol, liquid fuels, hydrogen, and carbon nanofiber, etc. The two figures here show the conventional autosomal reforming of methane to syngas and compared with chemical looping partial oxidation of methane. For conventional autosomal reforming, there are several drawbacks. First is the highly energy-intensive air separation unit. Second is the mixture of natural gas and oxygen, which can cause the risk of explosion. Chemical looping, on the other hand, uses metal oxide as oxygen carrier that circulates through the system to transfer oxygen from the air to the fuel. So it can avoid the direct contact between the two reactants. As a result, the air separation unit can be eliminated and explosion risk can be mitigated. However, the success of this process highly depends on the oxygen carrier. Currently, the conventional oxygen carrier requires a temperature as high as 1000 degrees C. This can cause problems including sintering effect, carbon deposition, morphology evolution-induced mechanical strength deterioration. So it is of great economic interest to decrease the reaction temperature. Here are listed several required properties for oxygen carriers. For chemical properties, we want the oxygen carrier to have high oxygen carrying capacity, high conversions in both the reduction and oxidation reactions, high selectivity to syngas, and satisfactory long-term recyclability. For physical properties, we want the sample to have good mechanical strength, suitable heat capacity, and high melting points. It should also have little health and environmental impacts. Here I compared several widely used oxygen carriers for chemical looping processes, including lanthanum iron oxide, copper oxide, and nickel oxide. Among all of them, iron oxide is one of the promising oxygen carriers for chemical looping systems because it has a very low cost and a high oxygen carrying capacity. It also has a very high stability, which makes it suitable for chemical looping properties. However, the problem with iron oxide is that it has moderate kinetics, which limits its application. My research is focusing on iron oxide as oxygen carriers and developing more efficient iron-based oxygen carriers for syngas production. There are two major issues that need to be considered. First is the ionic diffusion. This is because the reactions in both reduction and oxidation are gas-solid reactions. So increasing the solid ionic diffusivity can increase the overall reaction rate of the oxygen carrier. Second is the active sites. As I mentioned before, methane molecule is very stable. It has very low polarizability and negligible electron affinity. So surface active sites are crucial for methane-involved reactions. Here I designed a nanoscaled particles as oxygen carriers for chemical looping systems. Nanoparticles can be a great fit into this system for two reasons. First, compared with bulk material, the size of the nanoparticles are much smaller. So the ionic diffusion of oxygen from inside of the nanoparticles to the surface are much faster than bulk materials. This can increase its overall reactivity. Second, the surface iron atoms are highly energy-coordinated. They show higher methane adsorption energy and can work as active sites. However, the problem with nanoparticles is that they are metastable and tend to aggregate, especially at high temperatures in a cyclic system. So to solve this problem, I used SBA16 as a support for the nanoparticles. SBA16 is a mesoporous material with 3D cubic pore. In its body-centered cubic structure, each mesopore is connected with its 8 nearest neighborhoods to form a multi-directional system of mesopore network via its macropores. Iron oxide nanoparticles are embedded in the mesopores. This designated structure is supposed to have a very high surface area and more active sites. It should also have a good resistance to heat due to the confinement effect of the support. Also, to obtain a clear insight of SBA16 supported iron oxide nanoparticles, another mesopore structure supported oxygen carrier SBA15 supported nanoparticle is also synthesized and compared with SBA16 supported nanoparticle. These two materials has almost identical pore size, but with different pore arrangement. This slide shows the surface analysis and process distribution of SBA16 before and after nanoparticle deposition. We can see that the two samples have almost identical particle or pore size distribution, which means the matrix of SBA16 maintained after nanoparticle deposition. The morphology of the sample is checked under TEM. We can see that nanoparticles are embedded inside of the matrix of SBA16. The particle size is about 3 to 5 nanometers, as we can obtain from high-resolution TEM. And from the lattice fringe, the particle can be identified as alpha Fe23. The selectivity of this sample is tested in the TGA with temperature programmed reduction from 3,500 degrees C to 430 degrees C. We can see that the sample shows a very low reaction starting temperature of lower than 400 degrees C. This temperature is more than 500 degrees C lower than conventional Fe23 sample. The syngas selectivity is about 95%. The conversion rate of the sample is also tested in the TGA with redox cycle test at 800 degrees C. We can see that the conversion rate of SBA16 supported nanoparticles is about 4 times higher than conventional Fe23 sample, and it is about 67% higher than SBA15 supported iron oxide nanoparticles. The stability of the sample is also tested in the TGA with redox cycle test at 800 degrees C. The result shows the 100 redox cycles. As we can see, there is no obvious decreasing of conversion rate during the 100 redox cycles, which means the sample has a very high stability. The morphology of the sample after 100 redox cycles is also tested in the TEM. We can see that the nanostructure of SBA16 still maintained after 100 redox cycles and 800 degrees C, and the nanoparticles can be seen to be embedded inside the matrix of SBA16. From high resolution TEM, we can see that the particle size is still 3 to 5 nanometers, and there is no aggregation of the nanoparticles. This also indicates that the sample has a very high stability. To have a better understanding of the difference between SBA15 supported nanoparticle and SBA16 supported nanoparticle, we used dynamic Monte Carlo simulation. The result here reveals that Iron oxide nanoparticles can influence the gas diffusivity by different molecular mechanics in its two different mesopore structures. The gas molecule in SBS-15 sample tend to be trapped by the nanoparticles located in the 2D cylindrical mesopore structure. On the other hand, the 3D interconnected pore of SBS-16 facilitate the gas diffusion and can decrease the trapping effect significantly. The two figures here summarize the dynamic Monte Carlo simulations. Figure A shows that the gas diffusivity in SBS-16 and SBS-15 with uniform particle size distribution. We can see that for SBS-15, the gas diffusion decreases dramatically with the increase of relative diameter of the nanoparticles. While for SBS-16, the diffusion is less sensitive to the particle size. This can explain why SBS-16 sample has a higher conversion rate compared to SBS-15 sample at 800 degrees C. Figure B here shows the gas diffusivity with varying particle size distribution. We can see that diffusivity in SBS-16 depends on the amount of the particles loaded in the macropore. So to sum up, in this research, we found that iron oxide nanoparticles embedded in SBS-16 sample shows a very low reaction starting temperature of lower than 400 degrees C, which is over 500 degrees C lower than conventional Fe2O3. And the sample shows a high stability at 800 degrees C, which means that the sample has a broad operation window of 400 degrees C to 800 degrees C. And we found that the conversion rate of SBS-16 supported iron oxide nanoparticle is 67% higher than SBS-15 supported nanoparticles, and it is 4 times higher than conventional Fe2O3 sample. And from dynamic Monte Carlo simulations, we found that the diffusion in SBS-16 sample is less sensitive to the particle size, and the diffusion in SBS-16 mainly depends on the amount of the particles that are loaded in the mesopores. In the end, I would like to give my acknowledgement to Dr. L.S. Ban and my research group. With that, I will be happy to answer any questions. Thank you.